Hey everyone, it is November 20th, 2019. Time's about 7:30 in the morning. It's about 41 degrees Fahrenheit out, which I believe is about 5 degrees centigrade. And it is Geo-Rant time number 114. This is just one of my favorite quotes by Reed. He is a British geologist, or was, 1889 to 1970. So he died before I was even born. But anyway, just a quick note, couple things. Sarah got me this awesome brown kind of flannel shirt for my birthday yesterday, which is really good, and it was awesome, and thank you. These Geo-Rants, when I do these are unedited because, we all make errors, and I generally don't script these. This is mostly from me knowing how to do things like my structural geology ones, like 113 when I was showing you how to make a predictive model in geology. That was all from the app. That was all based on what I already knew. But on occasion I will have visual aids like what I just showed you. And in this case I actually have note cards, so hopefully I won't stumble too much. And hopefully this won't be ridiculously long, but I had the feeling it's going to be. So what am I going to talk about today? Today I'm going to talk about the granite controversy or debate. What's that? See, a lot of people aren't aware of this. It's important to understand the history of a specific discipline of science just as much as it is to understand the science. And the reason for that is so we can understand how we got to where we are, how we corrected the earlier errors, why we developed theories the way we did as opposed to a different way, or why certain ones were accepted and others fell by the wayside. And that is something that is not really taught even at the college level. If you take a geology class, like if you take structural geology, you learn about structural geology. You learn about everything. I mean, they tell you how, the theories behind, the applications, but they don't tell you the history. Why is this the way it is? Why do we know this works? Sometimes that's not taught. Sometimes it is. Depends on your professor. But anyway, this is part of that history. The Great Granite Controversy. Believe it or not, relatively recently, up until, the second half of the 20th century, we didn't even know if granites were an igneous or metamorphic rock. You might be like, well, they're igneous, obviously. That's what I was taught. Yeah, but why have we accepted that they are igneous rocks? I actually developed a ton of note cards on this, and I was going to shoot this up north at the cabin, and I don't want to make this way too long. But basically, the granite controversy goes like this. Up until the late 1950s, so even before plate tectonics, like right before we accepted or developed theory of plate tectonics, we didn't even know granites are metamorphic or igneous. Why is this controversy there? Well, because usually in Europe, the cores of the mountains exposed, they're deeper than they are out here in North America, with the exception of some places on the East Coast in Canada and stuff like that. So basically you had a bunch of European geologists saying these granites are metamorphic from a process called metasomatism, which actually, and there's a reason why they thought that. And I'm going to show you here in a few minutes the reason why we decided that they were igneous, and that's going to come back to the metasomatism thing and metamorphic thing. But anyway, so in Europe they thought that they were mostly metamorphic, and in North America we tend to see exposed, like with the Rockies and stuff, that's our young mountain range, or even in the Midwest, even older ones, and some places they're not, but we tend to see the younger parts of the granites of these rocks. So we assumed that they were igneous because we saw things here, and I've seen them too. Just in Wisconsin, you'll see what we call not phenocrysts. Xenocrysts. Is that correct? Big chunks of host rock. As a granite comes through as a liquid when it's a magma, it might grab some of that rock that it's intruding and push it into, as it moves up, and then when that magma crystallizes into a granite, that chunk of host rock is still within it. That's what we usually see here. We see stuff like that. In Europe, what they saw were the core mountains. They would see things like gneisses just kind of gradationally transitioning into granites. okay? And plus, and this was a legitimate point that the people who thought, granites were metamorphic rocks had, is something called the room problem. And I'm going to touch on that now. I'm not going to go into detail on that because I could do a whole series on it. Basically, the room problem was, well, if these granites are all igneous and their magma's intruding up, how did they find the room to intrude upwards, and a lot of times without deforming the rock to the left or the right? That was a legitimate argument. Well, as it turns out, there are explanations for that. A lot of granites, like granitic veins and stuff, clearly follow fractures. We see that here in North America. But by the way, not all North American geologists thought granites were igneous. There were some that were on the side of the Europeans, but most of the North Americans thought that they were igneous. So you would see things like that. There really isn't a room problem either if that melt is hot enough that as it comes in to actually melt the rock it's intruding and incorporate it into the magma. That also, eliminates the room problem. But so how did we decide that almost all of granites are igneous? Well, this is where the science comes in. This is where geology really got its hold as an actual testable science, as opposed to just observational science. Some guys ran some experiments. Bowen was one of them back in the 20s, as early in the 20s, who showed us Bowen's reaction series, and I've done videos on that. And as rocks crystallize, you have a continuous and a discontinuous series. Well, one of those series, as the granite cools, plagioclase will exchange cations in its mineral structure to become K-spar. So that's a type of metasomatism, but it's derived from a melt. The rock is melted. I mean, Bowen actually melted these rocks to see how they would crystallize. So he developed that back in the 20s while this whole controversy was still going. But that was just to show you how things crystallize out of a melt. It didn't answer the question, are granites igneous or metamorphic? That would come later. So this is why in science, testability is important. Experimentation, confirmable observations are important, because until this, which I'm going to show you in a second, was released, basically the granite controversy was a philosophical argument. All right? Both sides had legitimate points, and both sides are correct. And that's the problem with philosophy. If your arguments are solid, you're both right. Well, you can't both be right all the time. There are some things that you're either right or you're wrong. This is not one of those things, though. But it's close. So Tuttle and Bowen, I believe it was Tuttle. Let me double check that here. Am I on the back? Yes. Tuttle and Bowen. This was released November 21st. So tomorrow's the anniversary, in 1958. All right. The origin of granite in the light of experimental studies in the, basically this is the plagioclase to K-spar reaction series. Okay. In a nutshell, that's what it is. It's a little more complicated than that, but it's probably not even an accurate description. But anyways, the origin of granite in light of experimental studies. All right. So this here, I'm taking this out. I purchased this because I've always wanted a copy of this, and I wanted the hard one. This is not a book. This is a paper. This is a very long paper. It is a 142-page paper without the references. All right? That's just without the references. And Bowen and Tuttle worked together to answer this question through experimentation. And unfortunately, Bowen died around this time. So he was involved in it, but he never really got to see the resolution of the argument. And here, I mean, we have the results, the methodology, how the experiments were, what they were done, how they were run, the results in here. So we have the observational data in this paper, and a part of developing a hypothesis or theory eventually will be a conclusion, which is the interpretation part. But this is all just the data part. And they did so much in this. I mean, they really were thorough. And they even, at the end, there's some black and white pictures of detailed petrographic analysis on these rocks. But anyway, they did such good work on this as basically put to rest the granite controversy, kind of. Well, for the most part. Through these experiments, they demonstrated that the vast majority of granites, if not all, could be derived from melts. So they are igneous rocks. Does that mean all of them are? Does that mean that some granites can't form through cation exchange from a metamorphic rock close to the melting point but not at the melting point? And those type of rocks are technically metamorphic. If they start to melt a little bit, then you get things like migmatites, and those are complex rocks in and of themselves. But the answer to that question basically is no, not under normal circumstances. If rock is metamorphic, it's close to that melting point, but nothing actually melts, you're probably not going to get much cation exchange. That doesn't mean it's not possible. And there are some people and some papers that relatively recently, I'm talking within the past 20, 30 years, that show that metasomatism and that the origin of some granites may actually be metamorphic, at least on the, like on the outer rims or something like that. You can Google it. You can find it. You can find just Google metasomatism granites. There's papers out there. But the vast majority, if not all, are igneous. Bowen's reaction series shows us that cation exchange does happen as a melt crystallizes. But if you're already in solid crystalline form, can you have that cation exchange? And we do know in chemistry that certain solids can do that. So it's not out of the realm of possibility. The problem is to do experiments under such high pressure and temperature without melting a rock and observing it long enough to see if there's going to be cation exchange is very difficult to do. It's not possible with modern technology, but it is difficult. Melting a rock is easy and watching what crystallizes from it. That's a lot easier. But so we've answered the question. The great granite controversy has been laid to rest. Back in the second half of the 20th century, the vast majority, if not all, of granites are derived from igneous rocks. The room problem is not really a problem, but it doesn't rule out the possibility that some metamorphic rocks can become granites without actually melting, although it may be very difficult for that to happen, and it may almost happen not at all. See, the reason why this has come back up again is because of something called the SIAM classification system of granites, the SIAM classification, and I'm not going to get into that in great detail here, but it basically, SIAM type granites are classifications of granites based on tectonic origin, not composition. And when this system was derived and still used, and I think it's a sloppy system personally. There's other letters that have been introduced and dropped because they don't make any sense, or they're parts of other ones. It's not a very good system. But tectonic setting, that SIAM or SIAM classification system has kind of brought at least some granites back into the debate, if you want to call it that. But until someone can actually do these high pressure, high temperature experiments without melting the rock, they're neither here nor there. Because the second you start to melt the rock, you have a magma. You have liquids, and liquids can exchange ions a lot easier than solids. All right, so that was the great granite controversy. Basically, in a nutshell, You had the Europeans saying they're metamorphic origin. They are metamorphic rocks. You had the North Americans saying they're igneous rocks. And there was a lot of back and forth for decades, actually going back to the 19th century, the 1880s on this stuff, until this came out in 1958. So I am doing this Geo-Rant because the anniversary for this is tomorrow, 58. So that's, this was 60, it'll be 61 years ago. Is my math correct? 2019 today. I can't even count today. Sorry, it's still early in the morning. But anyway, that's it. If you have any questions or comments or need clarification, please let me know. And I hope you learned something, and I hope you got a little history lesson about geology out of this.